Hello again. This is another video for chapter 4. So we are going to talk about, I hope you're doing well. So let me go to maxima and minima, because that's where we left off last time. So let's continue with this. So we're going to talk about using calculus to figure out the behavior of functions, whether the functions go up and down, whether they have, how do they behave at different given value, x value. Now, we study a little bit in algebra and pre-calculus, but calculus is much more powerful tool to deal with this problem, to answer this question, than algebra and pre-calculus. So we're going to see how we can use calculus to actually understand the behavior of a function. All right, so the first thing we want to do is talk about absolute extrema. Now, extrema is a plural word for extremum, right? So extremum means either a maximum or a minimum. And also maximum and minimum are singular, so if you want to say more than two minima, you say minima. So minima, minimum, maximum, maxima, extremum, extrema. All right, so absolute extrema are basically absolute minimum and absolute maximum. So we're going to talk about absolute maximum and absolute minimum. When we talk about absolute minimum and maximum, we are talking about a closed interval. So for example, in this function right here, this interval is closed. So this interval is from 1 to 4, and 1 and 4 are included. You see, 1 and 4 are included. So in this closed interval, if you notice here, you see that function values, every point on the function has two coordinates, right? Is the x coordinate and the y coordinate, right? And I'm making a big mess here. Let me clean it up. So we have at every point we have x coordinate and we have y coordinate. So for example, right here is a point right there, and the x-coordinate for this point, so the x-coordinate for that point would be, let's go to another point, let's go over here. So the x-coordinate is that, and the y-coordinate, of course, is way over here on the y-axis, right? So when we talk about maximum and minimum, or absolute maximum, we are talking about the y-coordinates, not the x-coordinates, but the y-coordinates. So out of all the y-coordinates of this function from 1 to 4, including 1 and 4, which y-coordinate is the smallest? Well, it looks like the y-coordinate for this point is the smallest, right? If I erase everything else here. So you see, y-coordinate for this point is the smallest. You agree? This is 0, right? And the y-coordinate for this 4 is the biggest. So this right here, which is 4, right, is called the absolute maximum of this function in this closed interval. And this right here, 0, is the absolute minimum of this function in this interval. Now, so this is the absolute min, and that is the absolute max. That means 4 is the absolute max, and 0 is the absolute min. But where do they occur? Well, absolute max occurs at 4, and absolute min occurs at 2, right? So there's two questions here. One question is what the absolute max and absolute min are 4 and 0. Another question we can answer is where do they occur? At what x values? well, at 2 and at 4, right? So that's the idea we want to talk about a little bit here. So so that's the definition. So in order to be absolute max, you have to be, right? So with this value, for it to be absolute max, it has to be bigger than all the other y values in this interval, and it is. And for that to be absolute min, it has to be smaller than any other y value. Now we also include equality. So even if, as long as this is greater than or equal to any other value, we call it the absolute max. And as long as this is less than or equal to any other value in this interval, we call it absolute min. All right? All right, so let's look at, this is an example. And so if we have a theorem, it's called, without proof here, we're going to state it, extreme value theorem. It says that if a function is continuous over a closed interval a, b, right? So if a function is continuous over the closed bounded interval a, b, then there is a point in a, b at which f has an absolute max, and there must be another point that f has what? Absolute min. That means if a function is continuous in a closed interval, let's say that, then it must have at least one. It doesn't say the, just an. So it could be more than one. So if we are in a closed interval, the function has to have one absolute max and one absolute min. For example, here, obviously absolute min is here, absolute max is here. But you can have a situation when the function could go up and down, maybe. Let's say this function. Well, this function has absolute max, but it has more than one. It has here one, here's another one, here's another one. So it's got 3 max. They're all absolute max, right? And it's got more than one absolute min. 1, 2 absolute min, right? They're the same. So you could have more than one absolute min or more than one absolute max. But this theorem guarantees that they must have at least one of each, right? So that's the idea. So let me continue here. Now remember, the function has to be continuous for that to be true, right? So let's look at some examples. Here, for example, this is one. Now in this example, as you see, it is not true that this function has both absolute max and absolute min. It does not have absolute min, and it does not have absolute max, right? There is no value you can say is the biggest, because this continues, and this continues down. But does it violate the absolute, the theorem that we just talked about, the extreme value theorem? No, because this interval is not closed interval, right? It goes from negative infinity to infinity. What about this one? Well, this one does have absolute max, which is that right there, but it doesn't have absolute min. It approaches 0 but never reaches 0, right? So the function, there is no value on the function that you can say that that's the min, because you can always find a smaller one, right, on each side, on either side. So this one doesn't, it violates the extreme value theorem, but the reason is that, again, this interval is not closed, right? All right, so let's look at another one. This one has absolute max and absolute min, and it has many, right? But it does not satisfy the condition of the extreme value theorem. So extreme value theorem doesn't say that all functions have to satisfy it. It just says that If a function is continuous, it must satisfy the theorem. But it doesn't say that all functions have to be, all continuous functions have to have, all non-continuous functions have to have. So it doesn't say anything about functions not satisfying the condition of extreme value theorem. It talks about the ones that satisfy the condition of extreme value theorem. They have to have one of each, right? One absolute mean and one absolute max. Now this function is not a closed interval, but does satisfy the extreme value theorem. It's got max and min. What about this one? Well, this one has an absolute max. Does it have absolute min? No, because this goes down, but you can get as close as you want to -2. So if you say the min is -1.9999, well, I come around and I add another 9. I say, no, that's the absolute min. And you say, no, this one is absolute min. And I say, no, this one is absolute min, right? So there is no way you can find absolute min here. There is no absolute min. Now, if we had this point filled in, right, if it was like that, then we could say this is absolute min here. But it's not. So this does not, of course, the extreme value theorem does not apply because it's not continuous, right? It's not continuous from 0 to 4. So the ones that don't have the condition of absolute extreme value theorem, then they can have 1, they can have 2, they can have none, right? Extreme value theorem doesn't say anything about them. Only talks about if a function like this one is continuous and closed, the interval is closed, then it must have an absolute max and absolute min, and it does. What about this one from 0 to 2, but not including 2? Well, right away, this is not what? This is not, first of all, closed, though, second of all, is not continuous in the interval. It goes to infinity right here. So this one has absolute min, but doesn't have absolute max. All right. So local extrema and critical points. Now, so we have absolute extrema, right? So we have absolute extrema, and we have a local extrema, right? Local. Now, local extrema has to do with points like this, for example. At this point, you can say this y-coordinate right here, right, from here to there, right, that y-coordinate, and again, I made a mess there, let me clean it up. So that y-coordinate here, from here all the way up there, is bigger than the y-coordinates right immediately around this x value here, right? So in this short kind of interval around it, we call it a neighborhood. In the neighborhood of this x value, all the y-coordinates are smaller than this one. So we call that y-coordinate a local maximum. And this one right here, if you go a neighborhood around 1, to the right and to the left, right? You have to be able to go in both directions. And you have to prove that all the y-coordinates are actually bigger than this. So the other y-coordinates are a little bit bigger than that. So this one is called a local minimum. This one right here is a local maximum. Again, why? Because if you go around here to the neighborhood of 2, that's the biggest y value. And it occurs at 2. This one occurs at 1. This one occurs at 0, right? So that's the definition of extreme, absolute extrema and local extrema, right? So let's talk about that, and you can stop the video and read the definitions. I don't want to just read them to you. You can read them yourself. I just want to explain what they actually mean. So here we have, if an absolute extremum for a function occurs at the endpoints, we're not going to call them local extrema, right? So this is not a local max. This is not a local, whatever. It's nothing actually. It's neither minimum or max. But this one is what? This one is actually a absolute max. But since it happens at the endpoints, we call them endpoint extrema. So it's an endpoint maximum right here, right? Endpoint maximum. So if an absolute extremum for a function occurs at the endpoints, we don't call them local, but we call them endpoint extrema. All right, so local extrema and critical points. All right, the points, they call them critical points because at these points, either the derivative of the function is 0 or the derivative of the function is not defined. So the points where either f prime is 0 or f prime does not exist, if there is a x value at which these occur, we say that is a critical point. So for example here, this 0 here is a critical point. Why? Because y prime or f prime, the derivative is what? Is 0. And there is another critical point here, you see? Because the derivative here again is 0. Because it's horizontal, right? The slope of the tangent line is 0. Here is another critical point. Why? Because the derivative does not exist. Remember, at a sharp corner, derivative does not exist. So these are called critical points. Now, there is a very important theorem in calculus. It's called Fermat's theorem. And it says that if a function is differentiable at a point C, so if you have a point C and the function is differentiable at this point, right? And the function has an extrema at this point, whether maximum or minimum. So if the function has either a min at this point, or if the function is differentiable and has a max at this point, right? Then, again, we say if it's differentiable, right? Then f prime at C has to be 0, right? Must be. That's what this theorem says. So if we have a function that's differentiable at C and it has a local extremum, either maximum or minimum, then f prime at that has to be 0, right? Now remember that this theorem doesn't say the other way around. It doesn't say that if f prime is 0, then we must have what? An extremum. That doesn't say that. It says that if we have an extremum and the function is differentiable at that point, then the derivative is 0 at that point. Okay, so this is one of the theorems that I want to actually prove. So let's look at the proof. So what the condition says, the condition of the Fermat's theorem says that f prime exists at C. That means this limit exists from the left and from the right, right? Because that's what, when we say f prime exists, that's what we mean, that this limit exists, and this limit exists, that means the left and the right limit have to exist. So given that, and given that, let's say there is an open interval such that there is a C, so there is an open interval around C, right? So here's C, and here's an open interval around it. In this open interval, let's say f of C is a maximum, right? What does that mean? That means f of C, so let's say f has a max here. That means f of C is the biggest f of x. F of C is bigger than what? Any f of x in the neighborhood. That's greater than or equal to, right? So for all x in this neighborhood, we call it interval I, right? So what does that mean? That means that if I take f of x and subtract f of c, I get a negative number. Why? Because f of c is bigger than f of x. Which means that the numerator of this expression is actually negative, right? Now, also if we are on the right of c, because when we say the limit exists, that means we can go from the right or from the left. So if we are on the right of c, then x values obviously are bigger than c values. That means x minus c has to be positive. That means the denominator is positive. So if the numerator is negative and denominator is positive, that means this fraction is less than or equal to 0. It's either 0 or is negative, right? All right. So that means we conclude that f prime has to be less than or equal to 0. But we could also argue the other way around. We can say, okay, what if we are on the left of c? Then we still have this idea that f of x minus f of c has to be 0. I mean, less than or equal to 0. Why? Because f of c is the max. We also have this idea that x now is smaller than c. So that means x minus c has to be negative. And if that's the case, it means that the denominator is negative and the numerator is also negative. What's negative or negative? Positive. So that means this fraction has to be greater than or equal to 0. So we conclude this. Now notice here, we concluded, based on the given information and the conditions of Fermat's theorem, we concluded that f prime has to be less than or equal to 0. At the same time, it has to be greater than or equal to 0. How is that possible? The only way that it is possible is if f prime is what? 0. So that is what in mathematics we call analysis. So in analysis, we prove things, right? And that's a simple proof of Fermat's theorem. So that means that Fermat's theorem says that if f prime at some point c exists and the function at c has a min or max, then f prime has to be at c has to be 0. Okay? That's the idea. Now, so x at c is a local extremum, right? So if x at c, based on this theorem, we can say, okay, if a function has a local extremum at c, right, and f prime exists, well, f prime has to be 0. Or maybe f prime does not exist, right? Okay, but f still has c, has an extremum at c. So if the function has an extremum at c, we can conclude that either f prime has to be 0, which is Fermat's theorem, or f prime at c does not exist, right? And it's one way from left to right. So that means if x equals to c is a local extremum, then x equal to c is a critical point. Remember, what's a critical point? At the critical point, either f prime is 0 or f prime does not exist, right? So note this theorem does not claim that a function f must have a local extremum at a critical point, right? We just say if there is a local maximum or minimum, then c is a critical point, not the other way around. Okay, and we're going to look at some counter examples here. See, here's a counterexample. F of x equals to x to the third. Now, what's f prime? 3x squared. And we know f prime at 0 is 0, right? See, f prime at 0 is horizontal and is 0. So, if f prime is 0 here, right, then if we assume that this is true from right to left, since C, which is 0, is a critical point, then can we say, since this is a critical point, we must have a min or max here? No. And in fact, we don't, right? There is no min or max here. That's not a local min. Remember, local min looks like, local min and max look like this. This is not a local min or max, because you can't go to the neighborhood and say, okay, this is the smallest or largest, right? So this is not a local min or max, and it is a critical point. So just because a point is a critical point doesn't mean we have one of these at that point. But if we have one of these, then the point has to be a critical point. No question about that. Okay? All right, so here are some examples. So here, this is a local max at C, and f prime is 0, right? Here we have a local max at C, and f prime does not exist, right? So here we have a local min, right? And f prime does not exist. Here we don't have a local min or max, and f prime at C is 0. Here we don't have local min or max, and f prime is undefined, right? So it's possible to have f prime 0 or undefined. That means it's possible that C is a critical point, but we don't have a one of those extrema, either minimum or maximum at that point. Okay? Now all of these are critical points, and we do have what? We do have one of the min or max at those points. All right, so it says find all critical points. So all you have to find is critical points. Critical points are points where f prime is 0 or f prime does not exist. So how do we find critical points of a function? Well, it's very easy. We just take the function, take the derivative. Here you go, take the derivative, right? There you go, this is the derivative, right? This is by this, at this point you should be able to easily take the derivative of that. Now we set it equal to 0 and see the values that make it 0. And this, if you factor it, you end up with what? X equal to 1 and what? X equal to 4. So at 1 and 4, we have what? We have critical numbers. Do we have any point where f prime is not defined? No, because f prime is a polynomial, and polynomial is defined everywhere, right? In fact, this is a polynomial, and polynomials are differentiable and continuous in their domain, which is all real numbers. All right, and this is the graph of this function, actually. Again, at the end of this chapter, we're going to actually do this by hand, but for now, we're just figuring out how to do different parts of these, the procedures involved in graphing a function. Okay, so here is 1. There's a critical number at 1, right? And there's a critical number at 4. And we see at 1 we have a local max, and at 4 we have a local min. All right? So find all critical points again. Well, again, we take the derivative. Here is the derivative. Set it equal to 0. And we can, set it equal to 0. So f prime equal to 0. So that equals to 0. either x is 0 or this is 0. And we end up with what? We end up with either x equal to 1, x equal to -1, if that part equals to 0. 3 cannot be 0, so we just ignore that. Or 2x equals to 0, which we get what? X equal to 0. So there are 3 critical points. 1, -1, 1, and 0. And if you look at the graph of this function, you see that for this function, here is one critical point, nothing is going on there. I mean, not in terms of extrema, right? No min, no max. And here's another critical point, nothing is going on there. No min, no max. But the 0, we have what? We have a min, right? We have a local minimum at 0. So you see, not all critical numbers actually are points where the function has min or max. If something else is going on here, we're going to get to that later. But for now, we know it's not min and max, right? Local min and local max. What about this one? Well, here you go. Again, we take the derivative. Derivative here involves the quotient rule. So derivative of the numerator times the denominator minus derivative of the denominator times the numerator divided by denominator's second power. Now, when we set this equal to 0, right, how can a fraction equal to 0? The only way a fraction is 0 is if the numerator is 0, right? Denominator cannot be 0, and it cannot make the function, the fraction 0, because it cannot be 0. So the only part of fraction that can make it 0 is this one. So we don't care about the denominator. We take the numerator, simplify it, right, and set it equal to 0, right? And we end up with what? We end up with just 4 minus 4x squared equals to 0. So x is either 1 or -1. So there are 2 critical points for this function, 1 and -1, right? Now, the critical points here, both of them, they happen to have what? A min at -1 and a max at 1, right? See that? Again, later we're going to graph these and see how we can get all the different types of behaviors you see here under control. But for now, again, we are just figuring out what the critical points are. All right. So locating absolute extrema. Let's say we are given a function and we are given a closed interval, and we are asked to find what? To find the extreme values, the absolute extreme values, the absolute mean and absolute max of this function in this domain. So in this part of the domain, closed interval. Well, it turns out that if you want to find the absolute max and absolute mean, all you have to do is, first of all, you have endpoints, right, at -2 and 2. So we're going to find the function values at the endpoints. So we're going to find out what these are. And then in the middle of the interval, we're going to find all the critical points. So critical points for this one happen to be this one and this one, right? So we're going to find f at that number, and we're going to find f at that number, and then we're going to compare them. So we're going to find f of x1, maybe critical point number 1, and f of x2, critical point number 2, and then we compare these numbers. The smallest one is the absolute min, and the biggest one is the absolute max. That's all. So it's very easy, right? So again, in the interval, first we find the f of n points, then we find the critical numbers, and then find function values at the critical numbers, compare them. Okay, so let's do that. So again, these are the steps. You can stop the video and read them. That's exactly what I just said. So let's do an example, which is the one we just talked about. So we're going to take what? We're going to take f of negative 2. Substitute f of negative 2 with the calculator. You get negative 0.08. F of 2 is 0.08. Second step is to find the critical numbers. What are the critical numbers? Well, we have to take the derivative. Numerator, derivative of numerator times the denominator, minus derivative of denominator times the numerator, divided by denominator to second power. It's already to the second, so we raise it to another second, we get to the fourth power. And again, how can this be 0 if the numerator is 0, right? So we simplify it, and we get that, right? For x squared cancels, one of these, so we get 3, negative 3x squared plus 1, or 1 minus 3x squared, the same thing. Okay, now we set it equal to 0, so this has to be 0. And if you set 1 minus 3x squared equals to 0, you get 3x squared equals to 1. So x squared equals to 1/3. So x is going to be plus and minus the square root of 1/3, right? So these are the critical points. So we're going to find f at 1, at negative square root of 1/3, and f at positive square root of 1/3. Again, you can use a calculator. So we get that number right here and this number right here. Now we are going to compare this one, and this one, and this one. You compare them. The smallest one is what? Is the absolute mean. The largest one is the absolute max. And it turns out to be this one and this one. Right? All right. So that's how you find them. Here's another one. Again, what do we do? First, we find f at 0, then f of 2. We got them right there. F of 0 is 0, and f of 2 is 4. F of 2 is that. So that's one number. Here's another number, so we got 2 of them. Now we want to find all the critical numbers for this. How do we find critical numbers? We'll take the derivative. Derivative involves 2 parts, 2x. Derivative of x to the 2/3 is, we keep the 3 here. So it would be 2/3, right? So it would be minus 3 times 2/3 times what? Times x to 2/3 minus 1. 2/3 minus 1 is negative 1/3. And this is minus 2, right? So it would be basically minus 2 over what? X to 1/3 positive. That's what we get right here when you take the derivative of that part. And the derivative of x squared is 2x. Okay, we can combine this, or you could just leave it this way and set it equal to 0. Let's combine them into one fraction, so we just have to deal with the numerator, right? So if you make this a denominator of x to 1/3, you would get x to 1/3, and you have to multiply x by x to 1/3. What's x times x to 1/3? Well, that's 1 plus 1/3 is 4/3, right? So that would be 4/3. So we write the denominator and subtract the numerators. That's what we get, right? If you combine these two. So now we set the numerator equal to 0, right? We get that. And that is basically move the 2 to the other side, divide by 2. So you end up with what? You end up with this, right? If you move the 2 to the other side and divide by 2, you end up with this. So we got x to 4/3 equals to 1. How do I get rid of that? I have to raise it to what? I have to raise it to 3/4, because 3/4 times, raise both sides to 3/4. 3/4 times 4/3 is 1. And I get x equals to just 1. But since you're raising to 3/4, Remember, m over n means what? Means nth root of a to m, right? So you're taking nth root. So when you take nth root and n is 4, that means you're taking an even root of both sides. If you take an even root of both sides, you're supposed to put plus and minus. So the answer is plus and minus 1, right? And so these are critical numbers. We also have another critical number because what? Because, let me clean up my mess. So we got two critical numbers here, but look at the numerator, the derivative. The denominator cannot be 0, and if it's 0, what happens? Then f prime is not defined. So we're going to take the denominator and set it equal to 0 to find when is it that f prime is undefined. Now in the other example we didn't have to, because the denominator was something positive that is never 0. That's why we didn't take that into account. All right, so x equal to 0 is another what? Is another critical number, right? So these are the critical numbers. There are 3 of them. So what we have to do, we have to substitute what? All of these in f. So we got f of 0 already, which is 0, right there. Now f of 2 is 4, and this critical number that we found ended up being one of the endpoints actually. So we already took it and took that into account, right? So the 0 is actually just ended up being what? One of the endpoints. That's okay. So we write it there. We don't have to redo it. We did it already. So we have to find f of 1 and we have to find f of negative 1. What's f of 1? F of 1 is negative 2. And what's f of negative 1? Not in the interval, right? Negative 1, is negative 1 here? No, so we don't have to really worry about that. It has a value, but we don't have to worry about it. It's not in here. So we just compare those 3, right? And looks like the smallest is negative 2, so that's the absolute min. And the largest, wait a minute. Why did I put 4 here? My mistake. F of 2 is actually negative 0.762. There you go. So f of 2 is that. So biggest one is actually 0 because these are both negative. And this is more negative, so that's the absolute min and that's the absolute max. Okay. All right. And again, clean up my mess. So this is the picture from 0 to 2, and notice that you see the max happens here and the min happens here, right? And that's the picture of this situation here. All right, again, I'm going to do another video for next 4.4. So keep this videos a little bit shorter so you can take a break and maybe come back and continue. So I see you next time. Take care of yourself and others. I see you in the next video.